Hey there, everybody. It's Professor McDonald. So the first question that was in my inbox is number 6 from GLA 15, rational functions. It says, given the rational function f of x equals quantity x squared plus 5x plus 4 over quantity x squared minus 4x minus 32, find any holes of the function. Right, now remember, holes of the function come from values that would make the denominator equal 0. But they would also be factors that cancel out. So we're going to factor both the top and the bottom and see if there are any factors in the bottom that would cancel out. All right, so the top factors to two binomials, both starting with x, and since the top has a positive end term, constant term, both of the signs in these sets of parentheses in each of these quantities will be positive, or both of them will be negative. This sign in the middle is positive, so that means these should both be positive. All right, so that's a good start. Then I want to look for numbers that will multiply together to give me 4, and also they need to add up to give me 5. So that would be the combination of 1 and 4. Oops. I was trying to circle. 1 and 4. Okay, the top is factored. The denominator factors, again, we have a lead coefficient of 1, so we're going to have two binomials that start with x. The constant term is negative, so I'm going to have one of each sign. And the middle term is negative, so that means that the larger number will go with the negative. Now I'm looking for factors of 32, numbers that will multiply together to give me 32, but will also add up to give me negative 4. Okay, so multiply to negative 32, add to negative 4. Okay, so we do 1 times 32, that's going to give us a distance that's too great. 2 times 16, same thing. 4 times 8, that would be perfect, right? So let's give the negative to the 8, since we know we have a negative in the center term, and that will give us, when we add negative 8 plus positive 4, we will get the negative 4 when we add those numbers together. So we're going to put the 8 with the negative and the 4 with the positive. Now notice that this term and this term divide out to 1. And so although negative 4 would make the denominator 0, it's not going to be an asymptote, it'll be just a whole, because it cancels, that factor cancels out. The x is also not supposed to ever be 8, because 8 would make the denominator 0 also, but that factor doesn't cancel out, so that's not a whole, that's an asymptote. So the answer here would just be there's a whole at x equals negative 4. Okay, the next question, number 21 from GLA 15, rational functions. So we have the rational function polynomial in the numerator is x cubed minus 3x squared minus 4x. The polynomial in the denominator is x squared minus 4x plus 3. What we need to do are all of these things down here. We're going to find the domain, the y-intercepts, the x-intercepts, the well, there's really only one y-intercept if it's a function. There can be multiple x-intercepts. We're going to find the x value of any holes. We're going to find vertical asymptotes, horizontal asymptotes, or oblique asymptotes. And remember, you're either going to have horizontal or oblique, not both. And oblique is another way of saying slanted. So let's begin by finding the domain. And when we find the domain, that'll also give us the answer for the vertical asymptotes and any holes of the function. So really the best thing we can do here is factor everything out. So let's start by factoring the polynomial in the numerator. So it's going to be x times x squared minus 3x minus 4 to get the GCF out. And then that quadratic will factor, since it has a lead coefficient of 1. We'll have an x in each term, in each factor, and then 1 sine of each, because the constant term is negative. The larger number will be negative, since the middle term is negative. So now we're looking for two numbers that multiply together to give us 4, and add together to give us negative 3. So that should be 1 and 4, and make sure that the larger number is negative. So that'll be the complete factorization of the numerator. Okay. I will also factor out the denominator, which is a quadratic with a lead coefficient of 1. So again, we're going to have two linear factors with x in each one, where we have a positive last lead constant term. So that means they're going to be the same sign. And since there is a negative in the middle term, we're going to have two negatives here. Then we need two numbers that multiply together to give us 3, and add together to give us negative 4. So that would be 1 and 3. The only way you can factor a 3 anyways. All right, now notice that none of these factors in the bottom or the top are the same. So there's no canceling, so there will be no holes, right? So we just answered part 6, or I'm sorry, no, part 4. There are no holes. So we answer D, N, E for does not exist. All right, now the domain would be all real numbers except for ones that would make the denominator equal 0. So notice that if we set each one of these factors in the bottom here equal to 0, we would have to restrict so that x cannot be 1, because that would make the denominator 0, and x cannot be 3. And since they were not factors that canceled, these are not holes, but they are asymptotes. And so those actually give us the equations for the asymptotes. So for the domain, we write it in interval notation. But for the asymptotes, we're actually going to say, you know, there's basically an electric fence at x equals 1 and at x equals 3. Those would be the equations of the vertical lines that would be boundaries for the function, right? And the computerized homework has x equals on the outside, so notice that you would have just entered the 1 and the 3 there. Then to put it in domain interval notation, it may help you to do a number line where you just roughly sketch out where those values are, and you put, you know, don't include those values, but you include everything but them. So it's outside of the arrow, you can think of it as, going forever. So it would be negative infinity, as you can see. This is like negative infinity down here. We'll write it out like this. From negative infinity to 1, then union from 1 to 3, then union from 3 to positive infinity. Okay, so that was 3 parts of this question all done just by getting this thing factored out nicely. Okay, so let's go on and see what else we can do. Okay, we've done this part, we've done this part, and we've done this part. So what about y-intercepts? Well, remember, y-intercepts are places on the y-axis that the graph will cross. And when you're on the y-axis, the ordered pair always has an x value of 0. So finding y-intercepts, very easy. Just find, there's only going to be one if it's a function, and this is a rational function. So we just need to find one point where the x value is 0. What's the y value that would go with that? So just plug in zeros for all the x's and see what's left. So the entire top, notice, all the terms are going to 0 out, and the bottom will just have 3. 0 divided by 3 is just 0. So that's why the answer for number 2 is just the 1 point, the origin, 0, 0. And then for the x-intercept, it's the opposite. The x-intercept, and there can be multiple x-intercepts. The x-intercepts will all have 0 for y. Okay. Now, obviously, we're going to have one x-intercept that is 0, 0. But what else? So what we want to do is we want to set the entire function equal to 0, right? So if this is like your y over here. So you're setting that equal to 0. Then you're solving for x. You're finding all the x values that would make this statement true. Now, with a fraction, it only really matters if the top is 0, because 0 divided by anything else is always 0. So really, it simplifies, this problem simplifies to just setting the top equal to 0. And in factored form is even better, since we do have the factored form all ready to go there. This makes it simple. So now using the 0 product property, if this were 0, the whole thing, the whole left side would be 0. Also, if this were 0, the whole left side would become 0. And same thing for this factor. Okay, so any one factor, remember 0 times anything makes everything 0. So setting each one of these factors equal to 0 gives us 3 different x values where you would have a y value of 0. Right? Just remember, you can set x plus 1 equal to 0, solve for x, and get x equals -1. So the point -1 comma 0 is a y-intercept. And also when you set x minus 4 equal to 0. And solve for x, you get x equals 4. So the point 4 comma 0 would be. And then of course just plain old 0 right here gives us the 0, 0. So we have 1, 2, 3 x-intercepts for this function. And that part is done. Okay, so again, as a first step, factoring everything out really does help with all the other parts. All right, now our horizontal asymptote or oblique asymptote, which one will we have here? All right, so the rule for horizontal asymptotes, there's 3 cases. If the degree of your numerator is smaller than the degree of the denominator, then it'll just be y equals 0, the horizontal asymptote. Do we have that here? Well, the degree of the top is 3. The lead coefficient or lead term has a power of 3 on it, so that's degree 3. And the lead term here is degree 2. So this is top heavy. If it was bottom heavy, in other words, if the heavier degree were on the bottom, we would say it was 0, y equals 0, horizontal asymptote. But that's not what we have here. Also, if the degrees were the same, we would say there was a horizontal asymptote, and we would just take the ratio of the two lead coefficients. So then the horizontal asymptote would have been y equals 1 over 1, or simply y equals 1. But we don't have either of those two cases here. We do not have a horizontal asymptote. Instead, we have a slant asymptote because the bottom is 1 degree less than the top. So if we were to divide the bottom into the top and ignore the remainder, we would have a line equation, y equals mx plus b, and that would be our slanted asymptote or our oblique asymptote. So what we're going to do is we're going to divide long division, but only until we have y equals mx plus b in our quotient. So we're going to take the numerator, x cubed. Oh, I guess I might need a little more room than that. Hold on. Let me write out the denominator first. X squared minus 4x plus 3 into x cubed minus 3x squared minus 4x. And then we'll start doing long division. So we're going to look at the first term of each. Divide the x cubed by x squared. That gives us x. That's the first term in our quotient, and half of what we need for our slant asymptote. Then we take that x and multiply it times the entire divisor, x squared minus 4x plus 3. And that gives x cubed minus 4x squared plus 3x, x cubed minus 4x squared minus or plus 3x. Okay, then we have to subtract this. So we're going to change all the signs. Then we have our new line, which is x squared minus 7x. Then we're going to look at, well, let's get a different color here. Okay, good. So we're going to do x squared divided by x squared, which gives us 1. And since all we needed was y equals mx plus b, we've got that now. So that is the equation x plus 1. That is our y equals x plus 1 is our slant asymptote equation. And this one's all done too. Okay. Okay, now to answer this question, you're pretty much doing a lot of the things you did in the last question, except for these are already factored out. We can see that there are no holes because none of the factors cancel from top and bottom. We can also see that there should be vertical asymptotes. So vertical asymptotes, which would be the red dashed lines in the pictures. We should have those at x equals -2 and x equals +4, because those are the numbers that would make your denominator 0. So that's going to be probably one of the biggest helpful things to notice, is where to look for the vertical asymptotes. That'll help us narrow things down a bit. So let's start with that and see if we can do some process of elimination here. Okay, so this first one has a vertical asymptote at -2 and at +4. So this one's a good candidate. The second one also has vertical asymptotes at -2 and +4. This one has -4 and +2, so that's not correct. So we can definitely rule out this one. This last one here, again, has vertical asymptotes at -4 and +2, so those are not right. It has to be one of these two, just based on where the vertical asymptotes need to be. Okay, now, which one of these would be right? Well, we can look for the y-intercepts pretty easily, right? The y-intercept, just one. There would be a y-intercept where x is 0. So plugging in x is 0 into our equation here, we would be left with just putting zeros everywhere there's an x. This would simplify to, in the top we would have +3 times -2. So that would equal, in the top, -6. And in the bottom, we would have +2 times -4. That would be -8, which simplifies to +3/4. So we have, if we look at where +3/4 is, which should be just a little bit to the left of 1, we should have a y-intercept. And I don't see one on here. Come to think of it, I don't see one here either. So that's a little perplexing. Let me just check my math here. Putting in zeros, I have +3 times -2 and +2 times -4. So yeah, -6 over -8, that's a negative divided by a negative, that's a positive. They share a 2 in common. So if you factor out the 2's and cancel them, you get 3/4. So yeah, there should be a y-intercept. Oh, no, I'm wrong. I'm looking right at it. It's right here. I don't know why I didn't notice that before. So yeah, there's the y-intercept. That's just under +1 for the y value. Okay, the x value, remember y-intercepts always have 0 for x and some value for y. And you know, that's the same thing as 0, 0.75. So that's just about right. Now you can see that there, right under the 1. All right, so that has to be the answer. It can't be this one. Okay. Another thing you could look at, though, is you could try to figure out where your x-intercepts are. Remember, your x-intercepts will occur wherever the numerator is going to be 0, because that would make your y value 0. So if I set this numerator equal to 0, and then set each factor equal to 0, I would have x-intercepts at -3, 0 and 2, 0. So notice that I do have x-intercepts at -3, 0 and at +2, 0. So we've got all the stuff we need, matches this function with this graph here. Hope that was helpful, and I'll look forward to seeing you in class next week for test, what is it going to be? Yeah, test 3 next week. So please take advantage of your SLC tutor so you can get some extra credit while you're studying. Hopefully I'll be back to be able to hold some office hours before we have our next test. I will keep you updated with my status. Take care. Have a good night.